Let's begin having a look at, we're going to do a little bit of review on vector direction here, and then we're going to talk about adding vectors. Okay? So, just follow along in your little handout there. It's more or less, I made this, I sort of revised this from an old one. If there's a mistake on that handout, let me know so I can fix it for next year. Would you please? If I've got to make a little boo-boo somewhere. So a vector is a quantity which has both magnitude and direction. We saw that yesterday in the little movie clip. Examples of vectors include displacement, velocity, acceleration, force. We saw that as well. To fully describe one of these vector quantities, it's necessary to tell both the magnitude and the direction. If you leave one off, unfortunately, I have to take a mark away from you. For instance, if the velocity of an object were said to be 25 meters per second, then the description of the object's velocity is incomplete. The object could be moving 25 meters per second south, north, southeast, or any other direction. To fully describe the object's velocity, both magnitude and direction must be stated. Otherwise, supervillain vector will not be happy. In order for such descriptions of vector quantities to be useful, it's important that everyone agree upon how the direction of an object is described. Oddly enough, we were unable to do that as the human race. Most of us are accustomed to the idea that up on a map refers to the northward direction and right on a map refers to eastward. Okay, most people get that. Have you ever seen, I think Mr. Dick had one, he had a map of the world, but everything was upside down. Have you ever seen something like that before? It's kind of weird. This is a mere convention which map makers have used for years and upon which we can all agree. But what if the direction of a vector quantity is not due north or due east, but somewhere in between? For such cases, it's important there be some convention for describing the direction of such a vector. We use the bearing method that has north at 0 with the directions rotating clockwise. And you can see that in that little picture at the top there, right? See it? Okay? And I thought, you know what? It might be interesting to see what Wikipedia says about bearing. So I made a link to it, and I read it. And for Wikipedia, it actually was pretty complex. Bearing is a term used, for example, in navigation, although it can be used to refer to simply our direction of motion. Bearings can be measured in mils or degrees. In navigation terms, bearing is perhaps more usually the angle between our forward direction and the direction from us to another object. It typically refers to the direction of some object seen by us compared to our current heading. In other words, it's simply the angle between our forward direction and a line towards the object in question. So in other words, if I'm going straight ahead, I'm trying to go to the door, that's the bearing there. That's difference, right? The term can also be used to mean the absolute compass direction of an object as seen by us. In aerial terms, bearing means the actual compass direction of the forward course of our aircraft. In land navigation, bearing means the angle between the line connecting us and another object and a north-south line, or a meridian. And the U.S. actually calls it an azimuth. Where is it? Right there. U.S. Army defines the azimuth between point A and point B. So it gets kind of confusing real quick. Right? Okay? That's okay. We're going to make it simple. Don't worry about that. Okay. So in order for such descriptions of vector quantities to be useful, it's important that everyone agree upon how the direction of an object is described. Well, clearly, by our little visit to Wikipedia, that is not really the case. We'll have to agree as a group in here of how that's going to work, and basically I'm going to tell you, and you're going to agree to it. It's kind of like terms of service, you know, like iTunes, just check. You have two choices, either to agree or see you later. Most of us are accustomed to the idea that up on a map refers to north, and I said that already, didn't I?
Yeah. Better edit that part out.
I'm going to have to edit that part out. Blah, 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 blah. There's that picture again. That's weird. Okay, edit that. Okay, well, here's another link. This comes from NASA. Knots and nautical miles, blah, blah, blah. Latitude, longitude. You guys know a little bit about that, I think, right? Okay. Compass directions. Now, here's something that you might not know. It's kind of interesting. In navigation and surveying, all measurement of direction is performed by using the numbers of a compass. A compass is a 360-degree circle where 0 and 360 is north, 90 is east, 180 is south, 270 is west. Runways, when you go to the airport, runways are laid out according to the numbers of a compass. A runway's compass direction is indicated by a large number painted at the end of each runway. A runway's number is not written in degrees, but is given a shorthand format. For example, a runway with a marking of 14 is actually close to, if not a direct heading of 140 degrees. Well, your runway number tells you what direction you're taking off or landing. This is a southeast compass heading. A runway with a marking of 31 has a compass heading of 310 degrees. That is a northwest direction. For simplicity, the FAA, Federal Aviation, rounds off the precise heading to the nearest tens. Okay, so us physicists, us academics, sig figs to 2 decimal places. The FAA, kind of a little bit more important than me in a high school classroom, when they're landing an airplane and maybe 300 or 400 people's lives are at stake, they round off to the nearest 10. That's all I'm going to say about that. Yeah, it seems to work just fine. For example, runway 7 might have a precise heading of 68 degrees, but we'll round it up to 70. Good enough. Each runway has a different number on each end. Look at the diagram on the left. One end of the runway is facing due west, while the other end is facing due east, right here. See? The compass direction for due east is 90, or 9. All runway directions follow this directional layout. The runway would be referred to as runway 927 because of its east-west orientation. In fact, if I go here and put my mouse on 27, where does it point? 270. Okay? So this is like coming in this way. Right? You're landing on runway 27, meaning that you're headed west. It's a nice, quick thing for pilots to rig. Oh, landing on 27, or I'm coming in west. I got to look for runway number 27. They get it. They get it right away. Over here, number 9 points east. See that? Kind of neat. Anybody ever been out to the Dauphin Airport? Anybody know which way the runway runs out there? I have no idea. Okay. Theron, 6 plus 8? Sometimes. Sometimes. Most of us are accustomed to the following form of math, where Theron says 6 plus 8 is 14. But if I said, no, Theron, sorry, 6 plus 8 is equal to 10, 2, and 5. And any other number in between. You'd probably shake your head and wonder what he's talking about. When we become students of physics and approach the task of adding vector quantities, we soon become aware of the fact that the addition of 2 vector quantities of magnitude 6 and 8 will not necessarily result in an answer 14. They might not. How's that going to work? That's not going to be so easy, is it? Hannah's already worried. I can tell. She's worried. The rules for adding vector quantities are different from the rules for adding 2 quantities arithmetically. When I say arithmetically, what do I mean? It's just plain old adding like you did in grade 1, grade 2. Arithmetic is 6 plus 8, 14. Arithmetic 6, number 6. The arithmetic 8, number 8. But we're not talking about 6 and 8 numbers, we're talking about vectors. And if they're vectors, they also have to have a direction. A direction, exactly, Steve. And therefore, I have to also do what to the directions? If I'm adding the numbers, add the directions. How do you add directions? Vector are the quantities that include a direction. As such, the addition of 2 or more vectors must take into account that the quantities being added have a directional characteristic. There are a number of methods for carrying out the addition of 2 or more vectors. I will give you the easiest to start with. The most common method is the head-to-tail method of vector addition. Highlight that in some fashion. Did I remember where my highlighter is?
It's on the left, it's on the right side.
It's not, I don't think it's up here, eh? Okay, so head-to-tail method. Using such a method, the first vector drawn is drawn to scale in the appropriate direction. The second vector is then drawn such that its tail, right there, is positioned at the head of the first vector. Do you guys have that picture on yours?
No.
You should draw it. You should also write in, this is the tip or head, and this is the tail, right? Right there. The point of the first arrow touches the start of the second arrow.
So the tip and the tail are the same thing?
No, this is the tip of the first one, right? This is the tip of the first one, and this is the tail of the second one, right? Tip is the front, the pointy end. Tail is the non-pointy end. If I could use technical language like that.
Yeah.
The sum of 2 such vectors is then represented by a third vector which stretches from the tail of the first to the head of the second. And this third vector is known as the resultant. Actually, you know what? Now I remember, I was hoping that the supervillain in Despicable 2 was going to be called resultant, because he would be the combination of 2 supervillains, Vector 1 and Vector 2. That would have been a better joke. There'd be very few people that got it though. It is the result of adding two vectors. The resultant is the vector sum of the two individual vectors. And every time I say that, I can't help myself but think of first year university. It was fall of 1987. And I was in linear algebra with Professor, wait for it, Quackenbush. And that was my third class of the morning, and I was pretty tired by that time. And when he started yammering on about vector sum, I pretty much tuned out, and that was the end, and I was falling asleep. Whenever I read the words vector sum, I think of him. Of course, the actual magnitude and direction of the result is dependent upon the direction which the two individual vectors have. That's what it should look like. In red, what's that called? Resultant. Okay, and you should be drawing that picture now if you haven't done so already. Okay, the resultant starts at the start where you started drawing and ends up here. Okay, now I'll pause here for a second while people are drawing, and then I will tell you one of the most common mistakes that people make. Don't make this mistake. Students say to me, Mr. Bennett, you always say tip to tail. Okay, yeah, right. Then they do this. They go vector 1, they go vector 2, and then they think, oh, tip to tail, so I'm going to go like that. They like to complete the circle. Too bad it's wrong. Don't do that. The only thing that has to be tip to tail is the ones you're adding. This is the tip to tail I'm talking about. Then your resultant is where you started and where you ended up. Think about going for a little walk. If you started here, and you walk like this, and then you walk like that, what is the result of your little walk? The same as if you just followed that. Okay? So do not do tip to tail here. Just here where you're at. That make sense?
You put the arrowhead on the other side, or no? What's the right for?
Well, this point should be exactly on top of that point, right? Now, obviously, when you're drawing, you're going to make little tiny mistakes, and that's fine. Right? I'm not worried about that. Are we good? Okay. You know what? I want to show you something else. I should have had this loaded up. Should I close a few off? Like Despicable Me? We don't actually. Oh, you want to probably watch that one again.
Yeah. Well, we want to see the whole thing.
Okay, so here's a vector. Here's a vector. See if I can do this. Let's see if I can do this. I learned how to do this the other day. There we go. Okay, so I've done what to them? Put them tip to tail, exactly. And now the resultant is going to be... Oh, what's up with that? Should it be there?
No.
Well, if I move it to here, look at that. Now, this brings up a good question. Is it okay that it's over here? Well, the answer is still the same. Like, that vector is the same because all it has to be is it has to be the correct length in the correct direction, so that's fine, but it's really not graphically placed very well, is it, right? Okay, so it's right there. Now, if I were to grab this guy right here and go like this, see what happens to the resultant? Okay? So now, do you get, right? Like, if I can line that up, if this was 6 and this was 8, what would the green one be? 14. But if that was 6 and that was 8 and it was like this, would that be 14? No. It wouldn't be 14 anymore, would it? You can't just add the numbers together. You've got to add the directions. Don't worry about any of this mumbo jumbo up here. Okay. This principle of head-to-tail addition of vectors is illustrated in the animation below. In each frame of the animation, a vector with the magnitude of 6, in green, right here, here's the 6, the green one, is added to a vector magnitude 8 in blue. The result is depicted by the black vector, which is going around and around, which stretches from the tail of the first to the head of the second, right? Now, when the green goes all the way around, and I'm going to do this here, I'm just going to open this one up here. Right off the start, you got 8 in blue, you got 6 in green. What's the total? 14, like Darren said, right? But as it plays, as that 6 goes somewhere else, what happens to the value of the black? Keeps changing. Like right there, the resultant is 7.2 newtons. 7.2 newtons. We're adding force vectors here. You're right, should have been. Okay? What's the biggest value the resultant can be? 14. What's the smallest that it can be? What's the smallest that it can be? 8 forward, 6 back, right? Now, one thing that you might notice is, let's look at the direction here. Let's go all the way to the end here. Okay, which way is the resultant? And what does it show for direction here? 0. Note that a math person made this. East is at 0 degrees. When you get into probably grade 12, and if anybody knows, anybody know what the unit circle yet? Okay, the mathematicians like to do this. They start at 0 over here at east. Why is Jake texting me? Question. Okay. 0 is east, 90 is north, 180 is over there, and 270. That's only true in the math world. Yes, the mathematicians and the physicists, for whatever reason, couldn't get together and get it right. It has to do with the unit circle. It has to do with finding square root without calculators back in the 40s. A lot of history going on there. I'm not even going to get into it. But just be aware, it's different in math.
Would it be any different if math shifted it?
It's just a math. It'd be like changing red lights to mean go. It's just too big of a. It's too big of a convention to change. Yeah. Okay, moving on here. How much time do I have left? A little bit. As can be seen from this animation, 8 plus 6 could be equal to 14, but only if the two vectors are directed in the same direction. All that can be said for certain is that 8 plus 6 can add up to a vector with a maximum magnitude of 14, minimum of 2. Are we good with that? Okay. Does the order matter? Does the order that you add the vectors matter? Yeah. How do you know? Because it says so. And I always tell the truth, right? I better prove it. Only 90. I might not have been telling the truth about that. The summative result. Now when I say that, then I think it's Quackenbush again. Summative result, in other words, when you add two of them together, summative result of two of our vectors can be determined by a process of vector addition. The most common method is graphical head to tail, blah, blah, blah. We've seen this, blah, 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 blah. How do I find the result? How do I get it, Mr. Bennett? How do I get the answer? You take out your protractor. You take out your ruler and you measure. That's how you do it. You do not go a squared plus b squared equals c squared. Why not? Because that's not a right triangle.
But you could use like sine law or whatever it's called.
Which one?
So sine cosine law.
Like sine equals opposite over hypotenuse? Or a over sine a is equal to b over sine b? Yeah, that one, right? Yes, you can. But I would recommend, because you guys are going to be doing everything by scale, I highly recommend the use of a circle thingy, a protractor. More into that right away. I'm trying to speed up a little bit here. Okay, now, this is really cool. I did this myself.
No way.
Watch this. The question often arises to the importance of the order. And you know what? Even after I show kids this, they still come to me a month later and say, Bennett, does it matter what order I do? And then I look at them like this. Okay? Because I've already taught you. The order does not matter. Let me show you. If the three vectors are added, let's call it A, B, and C, then will a different resultant be obtained if a different order of operation or different order of addition is used? Will A plus B plus C give the same result as C plus B plus A or B plus A plus C? Are all these A's the same? Yes. Are all these B's the same? Are all these C's the same? Well, let's watch what happens. A plus B plus C. Where's the resultant? There it is. Now, if I go B, C plus B, C plus B plus A, see how I put them tip to tail?
What? No, it's not. No, not again. No, not there.
It's not going to work. No. No.
I don't know if I've ever been more satisfied with a class. That totally makes the half hour that I spent figuring out how to do that. Totally makes it worth it. Play it again?
Yeah. So impressive. I didn't quite understand.
I didn't quite get my money's worth, eh? Well, I did spend literally, I probably spent 20 minutes. Thank you very much. I should have a tip jar out. The order doesn't matter. As shown in the animation before, the order in which two or more vectors are added does not affect the outcome. Does not. The resultant shown as the red vector has the same magnitude and direction regardless of the order in which the three individual vectors are added. I think you have a space there to draw that picture, don't you?
Yeah.
You're following along? Draw that picture of the three additions for me. Now, if you're a pilot flying in the wind, this is kind of important because the wind acts like a second vector. Observe the three planes in the picture below. Each plane is heading south with a speed of 100 kilometers an hour. Each plane flies amidst a wind which blows at 20 kilometers an hour. In the first case, the plane encounters a tailwind from behind and of 20 kilometers an hour. The combined effect of the tailwind and the plane speed provide a resultant velocity of 120. 100 in blue plus 20 in red. In the second case, the plane encounters a headwind from the front of 20. The combined effect of the headwind and the plane speed provide a resultant velocity of 80. Plain old arithmetic. In the third case, the plane encounters a crosswind from the side of 20. The combined effect of the headwind and the plane speed provide a resultant velocity of 102 kilometers per hour directed at an 11.3 degree angle east of south. And suddenly things got a whole lot more complicated, didn't they?
Yeah.
Okay? So yes, pilots need to know this stuff. They got to understand vectors. How did they get that 102? Well, they add them together. I didn't do this one. I stole this one. These three resultant velocities can be determined using simple rules of vector addition. In the case of the crosswind, the Pythagorean theorem, a squared plus b squared equals c squared, and SOHCAHTOA, sine, opposite of hypotenuse, cosine, adjacent hypotenuse, tangent, opposite adjacent, are utilized to determine the magnitude and the direction of the resultant velocity. In other words, you can use grade 9 now. Grade 10? I'll stop there. Okay? Actually, do you guys have a picture of this?